look ahead at the calendar. We'll have class and we'll start today, and you're looking at your pink sheet that I have in front of. And then, of course, we'll have class on Thursday. Holiday on Monday for Martin Luther King. We get to have class on this day. This is one of those cultural observance days. So your red day classes are doing the no new content story. This is a 2-hour early out because holy cow, wow, it's the last day of the second quarter. You're officially, once this date passes, considered a graduating senior. Like, after this date passes, we call the 9th graders rising sophomores. We call the 10th graders rising juniors. We call the 11th graders rising seniors. There's no term for you. You're just done. Gone. So we need to make sure that we're ready for this end of the quarter, especially since that's a holiday, that's a cultural observance day, and that's a 2-hour early out. And then teacher work day, and this is the first day of the second half of your senior year. What? So let's go ahead and take a look at the pink sheet, if you will. Today we're going to do one of those projects. We didn't do one for Unit 4, but I'm going to give you time to work on it today. If you finish it and you want to turn it in today, then that's fine. We're going to save the second half, the last half hour of class for the notes and then your homework. So maybe what we talk about in the notes will help answer some of your questions for the project. So that'll be due in addition to the homework. That's going to be due by the next class, and that project will be the last grade of your second quarter. I am going to return your tests and then the corrections for the curve will also be due. So we'll talk about that too. Okay, you will have a quiz on the 18th. That is going to be the first grade of the third quarter. So that quiz is going to go on third quarter. And then you can see what we go through as far as the derivatives, related rates, optimization. This is a great unit that we're looking at because we finally get to apply a lot of things that we're doing. We've been looking at derivatives, like so what's this, so what, now what. I can memorize all those crazy rules, but if I don't know when I need them and how to apply them, what good are they, right? So that's what this unit is. I'm going to encourage you to, on the back of your old assignment sheet, we again have that vocabulary, or those pictures. So if you're looking for what can I do to improve my grade, that's always my favorite conversation that I have with kids. They're always like, Mrs. Glazier, what can I do to improve my grade? And I'll say things like silly things like pay attention in class, ask questions we don't understand, and do your homework. And they're like, no, I don't mean that. I mean, like, what can I do to improve my grade? I'm like, well, pay attention in class, ask questions you don't understand, and do your homework. I'm like, no, I mean, like, other than that. So you do have some extra credit opportunities. Each of these ends up being worth a missed homework, per se. So your expectation is to take a look at each of these visuals from your unit and tell me what they're all about. And the better an explanation, the more points I give. The weaker the explanation, the less points I give. Make sense? And I don't want the pink one, because the pink one's going to be on the third quarter. that make sense? So I don't want the yellow one and I don't want the green one because they were from the first quarter. So we're okay with that, right? We get that? All right. Any questions about the schedule? Any questions about what's due? By the end of class period today, I'm going to save the last 35, 40 minutes for starting the notes, and then we'll pass back the test right before the end of the day and give you a chance to ask some questions. If I wait for Stinger, that's way too long. I don't see you guys for Stinger until next week. So we're not gonna do that. We'll pass them back today. Sound okay? Right? Fabulous. So we're talking about some pretty cool stuff today. And that is like this. Here's my favorite frog. So when I toss Mr. Froggy up in the air and I catch him, he theoretically doesn't travel. He theoretically doesn't travel horizontally. He theoretically travels up in the air, and then I catch him. Everybody okay with this? All right. So please tell me why. Tell me why the graph of my dear Froggy looks like this. If he does not travel left to right, I'm not throwing him at Jacques, I'm not throwing him at Catherine, I'm not throwing him at, I'm just up to myself. To myself. Because the x-axis is time. Because our x-axis in this story can represent time. And time is one of those never-ending things. It keeps going and going and going. It doesn't stop. So elapsed time keeps going, keeps going, keeps going. What do you think this represents? So I heard distance and I heard height. Whoever said speed, I'm going to ask you to hold on to that for a second. Distance from where? So look at where he starts. Right? Distance from where? So in Algebra 1, we struggle to teach quadratics and a lot of their applications because kids always think that we're throwing things and they think that this is the path of the frog as he travels from the thrower to the catcher. And we're like, no, 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 because that's distance traveled. That's a third story. If I've got time across my x-axis and I've got the height of the frog is what's measured on my y, he's not traveling anywhere distance. So theoretically, you have been waiting since Algebra 1 for the frog to go somewhere. Because now I have his distance traveled and his height and his time. For us to talk about all three of those things at the same time, we need calculus. So we're not going to do that quite yet. We're going to start slow. Now I heard somebody talk about speed. Like without talking about the frog, without talking about the project, without talking about the graph. Give me an example of a time in your life when you talk about speed. Driving a car. How do you measure speed?
The thing on the dash. Miles per hour.
The thing on the dash. And what does it tell you?
Miles per hour.
It tells you how many miles per hour that you go. So when you're looking at that concept of speed, when you're driving a car, you're talking about miles per hour. Any swimmers? A couple swimmers in here. I know Billy's in here. Are you talking about your speed in terms of miles per hour? No. It's probably, you're not measuring your miles and you're not, well, I know some of the races take a long time, but not an hour, right? So, and you usually do meter pools, right? So if we're talking about swimming, don't you think we talk about meters per second, right? You can talk about how fast you're going when you talk about your meters per second. I care a lot about the copy machine. Mr. Logan and I, do you know who Mr. Logan is? He teaches PropStat and he teaches geometry honors with me. He and I have an argument. And I think it's time that we start measuring things to prove to him that I'm right. So we'll have our copies to make, and we both teach 3 sections of honors, so we both need to make about 90 copies. I go to this machine here, and I feed it in, and I take my answer keys, and while it's going, I'll do my answer keys. He hates that machine. He's like, that's the slow machine. You shouldn't go to that machine. And I'm like, okay, well, which is the fast machine? Do you know where the fast machine is? In the library. Would you say the library is close to this room or far away from this room? I would say it's kind of far too. Now, if we're talking about the cafeteria, that's really far. Right? If we're talking about the library, it's like halfway there, right? Okay, so he says it's faster to walk to the library and feed those copies in and walk back than it is for me to walk here, feed the copies in, and go back. What do we care about? Right? So teachers want time. I want to make the most of my time, all right? So I would need to know what for each machine. Okay, so I want to know the number of copies per, and we would have to figure out, now I agree with him, the library copier is much, much faster, but then I have to talk about how long it takes you to walk to the copier. Here I've got 30 seconds. There I've got 3 minutes. So if the number of copies per second for the number of copies I'm making doesn't add up to at least 3 minutes, it's worth staying here. You know what I'm saying? So we're starting to talk about the different things in calculus that we're going to start measuring, and it's going to be in these terms of rates. When we're talking about throwing a ball up in the air, we end up with looking at our distance per our time measurement, and that is how we get speed. Our speed can be in terms of miles per hour, if I'm talking about driving a car. Our speed can be in terms of meters per second, if I'm a swimmer. My speed can be in terms of number of copies per second, if I'm talking about a copy machine. So your speed is going to be whatever you're measuring compared to the elapsed time. Does that all make sense to you? Okay. So, with that background story, here is today's task with your group. And you're welcome to sit with and work with who you want. There's a little bit of a warm-up when we're talking about, you're welcome, when we're talking about taking the derivative, kind of get your heads back in that. Wait a minute, what? What's the derivative? Tell me about that again. I don't remember, I don't understand. So why don't we just complete these 3 warm-up problems together, and then we'll come back and check in a minute. So, and once you're working back, Time that it's over the test too. And then,
No, I
I
can't
don't,
do that.
so,
Yeah, literally can't do
Thursday would be fine. So if you feel like you need to, oh, just first, you can do that. Whatever makes sense for you, okay?
I just grabbed it. I was like, thank you. I didn't realize what it was. I gave it to you in the seat.
What is this beautiful?
I really needed it. I was like, thanks. I was like, oh wait.
Yeah, but like, this is not.
Okay, so let's go ahead and talk about what we're looking at here. Finding the derivative of each of the following functions. Couple things to remember. Making sure that you use correct derivative notation. Your exponent comes out. Applying the power rule. If it's easier for you to think of this as 3 times x to the 1/2 power, then I know that I wind up with 3/2 times x to the 1 less power. The derivative of a constant is going to be 0. So I can go ahead and write that as f prime of x is equal to 4x cubed plus 3 is in my numerator, 2 is in my denominator, as is the square root of x.
So why is it 4x? Isn't it 3x?
Where? Here? Because this exponent comes out front, right?
That's what I wrote.
4x? Yep. Kind of dust off those cobwebs, right? You're like, wait, I gotta find the derivative. All right. When we're talking about finding the derivative of our s function, s prime of t is going to be equal to 8t plus 8. Everybody okay there? Finding the derivative of this one, x to the 0 is 1. Anything to 0 power is 1. We all okay with that? All right, here's what you're working on today. Stretching your brains. Miss Holloway is playing catch with her best friend, herself. We need to get Miss Holloway some friends. She throws a tennis ball straight up in the air, and the height of the tennis ball is modeled by that function. T is time in seconds, and the function S is the height or the distance of the ball from the ground in meters. So here's the graph of the function. So here's Miss Holdaway holding the ball. In her hand. And then she's going to chuck it up in the air. And remember, when she throws the ball up in the air, the ball goes up and the ball comes straight down. Why do I see this curve stretched out this way? Because we're talking about time. So I'd like you and your groups to talk about what our horizontal axis represents. And I want to make sure that you talk to me about, units. I want to make sure here you talk to me about units. And when you're talking about our average speed, remember what we talked about as far as speed representing that 1 unit compared to another over time. And I want you to show me what that looks like on the graph. All right. So then you and your group mates are going to talk about the instantaneous speed. And you can call that at 3 seconds, making sure you include units. The key in this entire chapter is going to be that we talk about units. And then I want you to talk about some ideas of speed. You're going to get into a conversation about velocity and so on. So with your group mates, I want to hear you talking and sharing and thinking and putting your very best effort into quality answers so that when you submit this, I am compelled to give you the highest of points, therefore supporting your calculus second quarter grade. Sound okay? Off you go. Have fun.
Number 1.
So when we're talking about applying these things that we've been referencing, position, velocity, and acceleration, that's all by varying ideas of our degrees or taking our derivatives of them. So when we're starting to look at each of these graphs, if our ball is starting here, and remember the position of the ball is just going up and then back down. This concept here is because time continues to go. So when I plot the height of the ball is actually not traveling left, right. The ball is traveling up, down. That's kind of important that you understand that. Everybody with me on that? Huge mental thing for the algebra 1s to understand when we start doing quadratics way back in algebra 1. Okay. So when we start talking about velocity, in your project you're talking about the speed of this ball, but the reality is your speed knows no direction. Fast is fast, slow is slow, no matter which way you're going. So when we talk about speed, we're looking at a concept of a distance traveled compared to time, but the reality is that's actually velocity that we're looking at because it can have a positive and a negative sign about whether or not our velocity is positive or negative. When we take the derivative, and again, when we think about taking the derivative, you're talking about that tangent line that is at this point. And I want you to think about this tangent line potentially going from being super steep to being flat to being negative as it's going through. So this tangent line for this curve ends up changing as we go. So for each input x value, that slope of the tangent line here is increasing, then it flattens out, then it's negative. Stop for a minute and look at this graph and see how that relates. This velocity is pretty steep. It's a higher value here. That point right there is where the frog initially gets that push up when I go to throw the ball or the frog. I get to throw it up and it's going faster right here at this moment because it has my energy, that push. And it's slowly losing speed as it goes up. How come it's losing speed? Gravity, right? So that energy is transferred, right, to potential. So now it's up here. So here I want you to think about that velocity. How fast is it going? 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 What's this here represent? Right, that vertex, right, that apex, that top of my curve. Right here is where my velocity is what? 0, right? So what happens is I give the ball a push, I give the frog a push, and he's up real high, and for that split second, that one moment, he stops going up and then begins to come back down. What's happening as he's traveling past this point? What's happening here? What's happening here? He's gaining speed, right? Isn't he speeding up as he's falling? Isn't he going faster right here than he was here? Because he's gaining speed as he goes. So we see him going at his absolute fastest. We see this frog going at its absolute fastest right here and right here. Those are the fastest speeds, that highest velocity. This is when Froggy's going up because his velocity is positive. This is when Froggy's going down because he's coming back down and falling. Everybody okay with that? And you need to know that, and then maybe get some colored pens, because this point here where he's going up at 1 second, that's right here. This point here is going to be this point right here. And this point here, right before he crashes into the ground, is when he is going super fast. So what we're talking about, the velocity, is the derivative, that rate of change of the frog's position. Okay, moving onward, now we're talking about acceleration. When we talk about acceleration, because this velocity has this constant rate of change, this acceleration is going to be that second derivative, and that second derivative of a linear value is always going to be constant. So when we look at the relationship between position, velocity, and acceleration, we're talking about each having the derivative and looking at the rate of change of each one. So when we go ahead and we talk about that position function, that S of t, that is going to be where I am at any given time. This position function is my original function. My velocity function is looking at how that position is changing. And that's going to represent the derivative of our position function. So our derivative of our position function. When we talk about acceleration, I'm talking about now how the velocity is changing. So when I'm talking about how the velocity is changing, I'm going to take the derivative of velocity, which is the same as the second derivative of position. So it's interesting to see that velocity measures how position is changing and acceleration measures how velocity is changing. So velocity is the rate of change of position. If our velocity is less than 0, and we want to make sure that we understand that that is going to be a negative. If we have a negative velocity, then that means that our particle is moving in a negative direction. So when we talk about our particle moving in a negative direction, if we're talking on the coordinate plane, anytime our particle is moving left or down, we have a negative velocity. So anytime on the coordinate plane we have left movement or we have down movement, In real life, that's going to be a negative velocity. Anytime that my velocity is greater than 0, that's where my velocity is positive. And that means that my particle is going to be moving to the right or up in a positive direction. At that point, when your velocity is equal to 0, then we talk about that particle being at rest. And we say that it's not moving at that instant. So when that froggy spends that minor, minuscule amount of time where he's not moving up but hasn't changed to moving down yet, that velocity of 0, that moment in time, that instant, is where he's at rest. All right, so we were talking about the difference between velocity and speed. So when we talk about our average velocity, you're going to take the change in distance and you're going to compare that to the change in time. So when we have a second distance minus the first distance compared to that time change, doesn't that kind of ring true about slope? Doesn't that ring true about a rate of change? Doesn't that ring true about what we talk about with the slope of the tangent line, the derivative? We want you to be thinking about all those things at the same time. Speed is going to be an idea that is never negative. So it's kind of like absolute value. Your speed is going to be the absolute value of that velocity. So velocity is going to have that positive or negative, and that's where we're going to get that direction from. Are we okay? Yeah? All right. So the interesting thing is if velocity and acceleration are working together, we can look at them and see what's happening while we're talking about that ball changing or something going up or down or crossing the axis and looking at the values that we're looking at. If my velocity and my acceleration have the same sign, if they are both positive, they can both be positive or they can both be negative, then that means that my particle is speeding up. Whatever I'm talking about, my car's speed, the speed of the ball, the speed of the copier, whatever I'm talking about, that particle, whatever is moving. If the velocity and acceleration have the same sign, then I'm looking at something that is speeding up and going faster and faster. If they have different signs, then that means that the particle is slowing down. So here I have my value t. That is going to be my x value. That's my input value. And I can look at both my velocity and acceleration at each of these times. If I have a velocity of 3 and acceleration of -4, if those were my output values, would you say that whatever it is I'm talking about, is it speeding up or slowing down? Yeah, so this is going to be slowing down. So if you're talking about my velocity is positive, that means it's increasing, but it's increasing at a decreasing rate because it's slowing down. Does that make sense to you? It's increasing at a decreasing rate. All right, with your partners, do the next 3. Talk about it and see if you can conceptualize it. Go ahead. So if my velocity is 0, it's falling. If my acceleration is 7, that means it's going down at an increasing rate. If I have a positive velocity and a positive acceleration, that means that my value is speeding up. If I have a negative velocity, that means I'm falling, and I'm falling at a faster rate. Speeding up. I'm approaching that negatively. And that makes sense to us when we look here, because if we talk about our ball, our acceleration here is negative. So think about the ball going up in the air. Think about the frog. When I push him up, think about what's happening as the frog is rising and going up here. Is he gaining speed or losing speed? He's losing speed. My velocity is negative. My velocity is positive, but my acceleration is negative. So at this point in the journey, the frog is still going up in the air, but he's losing speed. He's going down. He's slowing down because my acceleration is negative and my velocity is positive. Right here is where things change. He goes up, 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 and then right here is when he starts to what? So his velocity is negative because he's speeding up. As he's falling, his change in time, his position, and then his acceleration is negative. This is a negative graph. So this is, does it make sense that he's losing speed going up because the signs don't match? He's gaining speed coming down because the signs match. Okay with that? All right. So we'll go ahead and we'll come back to here. Displacement, Brady and I were talking about displacement a little bit. When we're talking about displacement, we're talking about your net change in position. So an interesting conversation about this. Any of you run track? If you're a track star and you start here and you run, you run all the way around the track, and then you come back to exactly when you start, where you started, what is your displacement? You're like, you didn't get anywhere. You're like, I just ran a whole lap. You didn't get anywhere. So that concept of displacement is going to be the net change in position. If I'm teaching a class and I walk all the way over here, and then I turn around and I walk all the way back, and I end up here, my net change in position, my displacement, is just going to be the difference between where I started and where I ended up. Sound okay? All right, so here's a pretty cool picture. This figure shows the velocity of a particle moving on a coordinate line. Now remember, we're talking about the velocity, so we're already saying that this is the derivative of that position, right? So we're not looking at the position's height compared to time. We're talking about the speed at which it's moving. So keep in mind what happens when the velocity is positive and negative and 0. So what I'd like you and your partners to do is talk about, and I want you to find the intervals. So just like when we talk about intervals on the x-axis, we use our curves for our parentheses, not our boxes, because that value doesn't count until I leave it. Does that make sense? When we talk about increasing and decreasing functions, when we're talking about what intervals, we want to be using this to express our intervals, because once at this point, nothing's really happening. It's when I leave it that I'm talking about it. All right, so with your group mates, go ahead and talk about 1, through 6 together, and your mark is set, go. All right, so let's talk about this. When is the particle moving right? So it's moving right in a positive direction when my velocity is positive. So it's moving right from here to here because my velocity is positive. It's moving right from here to here because my velocity is positive. So anytime now don't think that that's a picture of where the particle is going. That's not its path. That is its rate of change. That's its slope of the tangent line. There's some curvy thing going on with this particle. We're looking at a graph of the derivative. We're looking at one level less. So this is all curvy, and its rate of change goes from being a positive increasing to it being a negative decreasing idea. Here is where that particle stops being in motion in a positive way and changes direction and starts having a velocity of negative. So make sure that you understand the because. The because is so incredibly necessary, and on your projects that you turn into me, without having a justification of the because, you're not going to get full credit. So making sure that this unit, we are so precise and careful about our units and about justifying why it is, and whether we're looking at the graph of the rate or a graph of the position. This is a rate graph we're looking at. So its velocity here is decreasing. Okay, and then of course it's moving right here and here too. Okay, when is the particle moving to the left or down from 1 to, I said 4.8. If you said 4.7 or 4.5, whatever, just as long as you recognize this value between 4 and 5. Why is it moving left? Justifying, getting used to saying because its velocity is negative. That means that it is falling or moving down. All right, let's talk about acceleration. Acceleration is the second derivative of position and the derivative of velocity. So we're looking at the slope of the tangent line. Well, this tangent line, because it's a linear function, that tangent line is, and the slope of that tangent line is going to exactly match this constant rate of change. So what's happening to the acceleration here? It's negative. Here the acceleration's positive. Here the acceleration's negative. So we're not looking at the output values. This is our velocity graph. The graph of the acceleration is going to look like something else. It goes from being negative to positive because we're talking about the slope of these lines. So it's positive from 2 to 6. It's negative from here and here. And I don't ever have any kind of horizontal constant part of the graph, so it's not ever 0. This particle has the greatest speed here at these two extremes. Because remember, I'm graphing my velocity. If I'm looking at that first part of the ball going up, it's going fastest the minute it leaves my hand. It's going fastest when it falls. The particle is speeding up when the signs match. Here. Speeding up. Here. Speeding up. When I have a positive velocity and a negative acceleration, think of that frog going up in the air. It's losing its speed. It's getting slower and slower, right? Whenever I have a negative velocity And a positive acceleration, it's losing its speed. When my signs match, negative, negative, positive, positive, that's when it's speeding up. Totally has to do with the signs. Sound okay? Yeah? So let me know, is this familiar to you because you've had physics? Is this similar to what you've learned in physics? Or talk to me. No physics takers out there? Are you in physics now? Are you doing something similar to this? Yeah. Okay, similar. So how did you do this without knowing what the derivative was? I'm so curious how the two courses match.
I took IB physics last year. I had those little formulas that they gave us.
So you were taking them through, you just didn't know what you were doing?
It was like 1/2 Washington square or something like that. We were given like what's our thing?
Does it make more sense to you now that you know what the derivative is? Okay. I don't know, I'm always curious.
I don't remember. I could actually go back.
That's where you have to justify by the signs, whether or not the signs match, whether or not they're the same. Does that make sense? So you have to keep writing them.
So what is 1 to 2?
Okay, make sure that you understand. So Stephen asked a great question. He's like, what do we write after that? Because you're writing down your justification. So when we're saying that the particle is moving left because the velocity over time is less than 0. When is it moving right? Because the velocity compared to time is greater than 0. Stephen, are you watching? Okay. So when the particle's acceleration is positive, negative, 0. Okay. The greatest speed, okay, here the because, it is speeding up because the signs of the velocity with respect to time and acceleration with respect to time are the same. Here we have because the signs of velocity with respect to time and acceleration with respect to time are different. Does that help? Awesome, thanks for asking. Okay, so your homework tonight, oops, I'm coming to my staff meeting. But your homework tonight is a little bit more of this and to finish your project. I left us about 10 minutes to return some papers. I have a ton of them to return. Corrections for the test. I don't know if any of you saw Miss Holdaway when you came in and had her little rant. She's like, I just spent all this time grading the kids' test corrections or the kids' retakes, and so many of them did worse. Yeah, I had that frustration earlier. So the whole idea of you doing corrections, and I would anticipate you by your senior year, you know what you know and don't, and you know what you don't know. So don't come in and take the retake if you haven't learned what you didn't get the first time. And if you're like, well, if I could have taught it to myself, I would have done it. Okay, then come in after school and ask questions. Or go back and watch the videos. Something's got to happen in between your two tries for the test. So I get real deep and picky with my geometry students, making sure that their corrections, that they've done it. With you guys, I'm assuming if you're turning in the corrections, that you've done the work. Nobody learns calculus by just watching. So So either you're doing the work or you're not. Okay. So come get please, and when you get your quiz, I'll make sure I give you your corrections. I just have some random papers. So Nate and Maria and Simon, Ricardo comes out, Adrian. Kara, Steven. Please don't talk while I'm returning papers. Everyone gets to give their name. Nadia. Jaden, Grace, Catherine, Kaylee, Caitlin. Nate, Kenton, Louisa. I need to try this in with the test. It doesn't count on the test. Billy, absent. Steven, Adrian, Yara, Ricardo, Kenton, Isabella, Grace, Kaylee, John, Simon, Grace, come back. Kenton, come back. Isabel, Simon. Oh, wait a minute. Simon, Catherine, Kaylee, Yara, Nate. Sorry, pass it to the right person. Nate, Steven, Ricardo, Grace. Grady. Chuck. Kenton. Veronica. Maria. Jaden. Adrian. Caitlin, Maria, John, Billy. All right, so I'm coming around with the exos. Hey, it goes like this. You have to turn in the test with YouTube, otherwise I can't see what it is that you're correcting. Your test. You want there's about 5 minutes left. So if you want to look over your paper, ask me questions, we'll talk about, go over.
We always have a 10 minutes.
Everybody does corrections for the test. After you do the corrections. If you do corrections, and they're right.
I've stopped.
Yeah, so the corrections for the curve. If you want a curve, you have to do corrections. And your corrections have to earn you the curve. So if your corrections are all wrong, I'm not curving it. Yeah.
Real quick, can you just explain this last one to me? I don't really understand.